Sweden. Both Thidé will tell us about something which, in a way, is connected with what people in quantum information call resource. This is a very popular word. Everything is resource in this area, including entanglement is a resource. So now we'll learn about a new resource in ordinary communication, and this new resource is angular momentum. As you know, frequencies are distributed already among various parties, so it's very difficult to get a band of frequencies, but as Bo will tell us, at each frequency we have a lot of angular momentum. So we can expand these resources quite a lot. Bo?
Thank you very much, Ivo. And,
the floor is yours.
Yeah, thank you. Thank you very much. And I'm very happy to be here. Thank you to Ivo and Sophia. They're taking wonderful care of me as I drive on Friday. The reason I'm here is that we met in Vienna a little more than a year ago, 2 years ago. We were both visiting Anton Seidinger in Vienna, and we happened to share an office, and that's the best way, you know, sitting across, chat. I'm sorry I wasted your time, but it was invaluable for me. So let me, so my name is Bo Thidé, that's how you pronounce it. It's supposed to sound a bit French, I don't know where it comes from. It's very strange. Probably, I would bet that I am the only living soul in this universe to this. So it's not, if you think it looks strange, it is, because it is strange.
And it's not spelled V-E?
No.
But that's not that rare name in Sweden.
No, that's rather common, that's the combination. So this is just, so I would tell you about
Since you might never use the last name in Sweden.
No, you don't.
Yeah.
Use the first name even to, you know, the Prime Minister, which is a dramatic change from when I was young. They called me Mr. Today in school. Imagine. So, but that's another seminar. I have been working at the Swedish
Institute. But you can mention
yeah. I got my PhD in theoretical physics in Uppsala, working on semi-classical techniques, geometrical optics, WKB, phase integral approximations. You might have heard of Sir Michael Berry. He was there often, so I met him already in 1977. We were working, our group, and he was working in the same area. Then I got my PhD, and I became what we call university lecturer, which is teaching, never sleeping, and I had 2 small children, so now I want to sleep more than 3 hours per night. So I joined the Swedish Institute of Space Physics, because then I can exercise my interest for experimental things, particularly electromagnetic things, and I have a passion for radio since I was 12. I got my first radio receiver when I was 12, and helped the neighbors fix their radios and TVs when I was 14 and things like that. Actually, this is also something that Richard Feynman is. That's the only similarity, absolutely not similarity between him and me. He's clever, I'm not, he was. And so I joined this, and so I did the research here. So this is a fully research institute directly under the Ministry of Education and Research. But also do my teaching, had my PhDs and so on at the Department of Physics and Astronomy in Uppsala University. But when you reach a certain age in Sweden, the rules are that you cannot apply for funding anymore. You can continue to do research, but you don't get any extra money. And my research, I need to travel, I need to buy some equipment, because I do mostly experimental things, even though this will be a theoretical seminar. So I'm now trying to establish some kind of relation with Europe. I've done that for the past 5 years, 6 years, 8 years actually. And I just recently submitted an application to the European Research Council. That's the only way I can get money. I don't want to stop. Who wants to stop? I mean, I want to do research until I die. It's for you young people. never stops. You like it all your life, so we are something. So in order to get some kind of possibility to travel like I am now, I joined up with something called Swedish ICT. ICT stands for Information and Communication Technology. It's a research institute which is formed like a company. It's a non-profit company. The majority owner is the Swedish government.
It's Aktienbolag.
Aktienbolag, yes. And Aktiengesellschaft in German.
I remember my Sweden.
Yes. And this company is non-profit and it's owned by 2/3 of the Swedish government and 1/3 by the Swedish industry like Ericsson and so on. And what they are doing is trying to take the latest discoveries in optics, radio, and to create some kind of new prototype. So I'm working for them, writing a little report, or a rather big report, for which will be the basis for yet another EU application. So with this long introduction, I'll just say again that I'm very happy to be here. And it's very nice to enter a building where, you know, there's theoretical physics, because that's what I really like. The most happiest moment in my life was when I was accepted as a PhD student in theoretical physics, and I entered this fantastic library we had. You know, I spent day and night in that library. You know the field. If you have been there, done that, then you know the field.
You mean in Uppsala?
Uppsala,
Where the
yes.
Copernicus library is part of?
Yeah, okay, yeah. So this is the Institute of Space Physics Logotype. This is the Uppsala
That's the
University.
other reason why this
This
hair
is-
of
this is the,
Copernicus was found.
This is a radiation diagram. This is a pointing vector, or the linear momentum density of a radiator which radiates angular momentum. You will see it later on, and this is a lot for that. So, sorry for this lengthy introduction, but let's start. So we have a challenge now, as Ivo referred to, and it even has a name, an American slang name, the spectrum crunch. The increasing congestion of radio frequency bands. This imposes serious limitations on the capacity and capability of existing wireless information infrastructures for radio science, and notably also radio astronomy, because radio astronomers, they need frequencies, you know, quiet frequencies, and you know, there's a fight for it, and a lot of money. And all the way today, what people have done, they've come up with enormously clever, fantastic engineering tricks based on the standard way of communicating, namely transmitting electromagnetic field, extracting the pointing vector, that I'll show you a little figure of, and from that pointing vector, which is an observable, get current running in an antenna, say, and then extracting the information, the modulation of that current. But the question is, are there other observables in the electromagnetic field, other conserved quantities? We know from elementary group theory, or elementary semi-elementary classical electrodynamics, that there are at least 10 corresponding to the 10 parameters of the Pythagorean group. Actually, nowadays we know that there are 84. People have found much more. Mathematicians have found 74 more for us. But today, we use typically only 3 or 4. So the question was, are there other observables, other physical conserved quantities in the electromagnetic field that can be used for communication? And yes, of course there are. So the question was that, and we say we think there are, and not only we, but other people too. So in order to achieve this, to try to get down to a new physical layer, as we say, forgetting about pointing vectors, or augmenting the pointing, including not only the pointing vector, but also other quantities. The pointing vector, I will come back to that several times. The pointing vector is the linear momentum carried by the electromagnetic field, or more strictly speaking, the linear momentum per cubic meter, the linear momentum density. Linear momentum is a consequence of the translational symmetry. It can only describe motions along a line. But we know that electrons, we know that electromagnetic fields can move around in any way we like. So the question is, why don't we use all the degrees of freedom? We only use 1 degree of freedom, essentially a scalar quantity, one component of an electric current. this ends up that when you do the analysis, you find out there is more to it. And the physical reason is very old, goes back to 1775. An Euler, because he showed that a complete theoretical analysis and description of the dynamics of an electromechanical system, for instance, the charges, currents in an antenna, and the associated electromagnetic fields, and the plasma, what have you, must take both the translational and the rotational degrees of freedom. Without describing, you cannot describe a general motion just in terms of straight lines, right? This is the simple, it boils down to that. So you have to take the rotational degrees of freedom into account. And the translational dynamics is described by linear momentum, and the time derivative of linear momentum is the force, and the force per surface unit is the radiation pressure. So these antenna actually, the traditional antenna operates on the mechanism of radiation pressure, pushing electrons up and down. It's a simplistic
But
picture.
when you measure polarization,
Yeah, right, absolutely right. Yes, I'll come to that. Because, so that's why I said, that's why I said 3 or 4. The fourth one is the polarization, but there are infinitely many more degrees of freedom, so to speak. Yeah, you're absolutely right. Very good. Yeah. So this is the point of that. But rotational dynamics is described by the angular momentum, and the time derivative of angular momentum is not force, that is torque. Force would make things go like this, and torque make things rotate. And when it rotates around its own axis, its spin angular momentum, that is polarization. But when it rotates around an external axis, which is also possible, that's the orbital part of the angular momentum. And this is the part that we're using, not in this one. So, the two parts, this is Euler's second law, 1775. After 35 years of discussion with Bernoulli, they agreed, yes, you cannot describe angular momentum in terms of linear momentum, which was the misunderstanding. The angular momentum has two parts, the spin part, like the Earth spinning on its axis, and the angular part, which is spin orbiting the Sun. And the same with electromagnetic fields. The polarization has two independent states, left hand and right hand, spin plus minus 1, that's it. So by using polarization or spin, you can double the capacity of a radio communication channel, or you can extract twice as much information about your radio source in an ideal case. But that's it. Whereas the orbital angular momentum it spans a innumerably infinite Hilbert space, which has dimension n can be any integer from 1 to 3, But of course, for high numbers, it gets expensive and complicated. But that's the idea. So let me just quickly remind you of the 10 Poincaré invariants, and these are densities. This is energy per cubic meter, so this is energy density. This is one conserved scalar. It's a scalar quantity, so it's one number. We have the linear momentum density, Poynting vector, or according to the Planck relation, divide this by c squared, and we have the Poynting vector. So the Poynting vector and the linear momentum density are identical except for the fixed proportionality constant, which is 1 over the speed of light squared. And this describes changes in the translational. This is the only conserved observer that's fully exploited today, because spin angular momentum is not conserved, the total angular momentum is conserved, the polarization is not conserved, but polarization plus orbital angular momentum is conserved. So that means. And the electromagnetic field angular or rotational momentum or momentum density, it looks like it has this expression. And you might think, well, it's just a matter of taking the radius vector from your source to your detection volume, protection point, and take this analytic expression you get up there far away and put it in there, but if you do that, you get 0. The funny thing is that, the electric field has 4 components, the Coulomb part, the 2 intermediate parts, which are, 2 are longitudinal, 2 are transverse, and they have the far zone. In Poynting vector far away, only the far zone part of the electric field, 1 out of 4 components, play any role, and the magnetic field is also the far part. However, the only part of the electric field that gives contribution to angular momentum in the far zone, infinitely far away, is the intermediate immediate field which falls off extremely rapidly. So already when the radiation leaves this zone where it's generated, only a few wavelengths away, everything is it's been stamped, it has been imprinted with this property, and it's carried all the way because angular momentum is conserved. It cannot, once you have twisted your beam, so to speak, you cannot untwist it unless you have, at least if you propagate in free space. It's a conservation law. Now this is using...
One problem with the angular momentum is that it depends on the coordinate system.
Yes, but so does linear momentum. But spin doesn't, you know. So spin angular momentum, that was in the previous one. The spin angular momentum, the photon has spin, it's an intrinsic property, whereas orbital angular momentum is an extrinsic property. And the same with linear momentum. So it used in photonics, spintronics, and now coming orbitronics. This observable is not fully utilized in today's radio, very, very little indeed. There is actually, so we have now one conserved scalar quantity, one conserved vector quantity, which is three scalar quantities, 4, 1, 2, 3, 4, 5, 6, 7. So there should be 3 more because this is a 10 parametric group. And the 3 more are the so-called loose momentum or center of energy, which is not used at all. And then there are another 74 that we have discovered among the physicists and mathematicians, starting 1961 with a very famous paper where they found a quantity which was called zilch, because I didn't know what it was, and now they have 84. And
Actually, they're infinitely many.
yes, but it depends on how you define it. Yeah, okay. And that's
Because each
yeah,
wave vector
can yes.
stays.
But if you have yeah, well, that's another seminar, and which you should give rather than me. But let's forget. I will not talk about it. But it tells us that we have some more extra. If we need something, we can try to observe this and get separated two possibilities, perhaps. So. Now,
Can I ask a question?
yes.
Concerning the definition of it. This is only if I have just one antenna which sends the information and the other person to pick it up. But that's not what is happening in communication nowadays, right? The X-dependence picks up the receiver and the emitter, so to say.
Yeah.
And how that would work in the array.
It works for the array. I will show you this picture that I showed that was made by an array of 16 antennas. So
16 towers, so to say.
yeah, 16, yeah. 8 in an inner ring. No, 24. 8 in an inner ring and 6.
That's irrelevant, 24. Well,
Yeah, but it was not just one. No,
so you can
no,
make it independent of the X.
no, let me back up and let me. Sorry to interrupt you, but I will.
No, it's okay.
And the chairman will stop me soon. You know, if I have an electromagnetic field generated in any way I like, it could be lighting up a candle, it could be from this, it could be a lightning, it could be the sun, it could be a radio transmitter with 1, 2, or 47 antennas, or just a piece of junk wire, and I feed some energy to it. That radio wave, that electromagnetic field always contains energy. I don't have to do anything, I don't have to prepare, I don't have to make any tricks for an electromagnetic wave to contain energy. I don't have to make any tricks for an electromagnetic wave to contain linear momentum. I don't have to make any tricks for it to contain this because it always contains all these detailed quantities. And these are the observables, directly observables. Fields are not observables. We'll come to that. Fields and observables, two different things. Radio works because it makes use of physical observables. The postulates of electrodynamics, the Maxwell's equations, or I use Maxwell-Lorentz equations, the microscopic version of Maxwell's equations, are differential equations for the fields E and V, which in fact are formally not directly observable, formally not directly observable. Formally indirectly observable, informally directly observable, but not formally directly observable. Freeman Dyson, whom I think most of you know, the fourth man behind quantum electrodynamics, but the one who never got the Nobel Prize tries to put a limit of 3. And this is what Stephen Weinberg said in an interview recently. The Nobel Committee fleeced Dyson by not awarding his work in quantum electrodynamics with the prize because Stephen thinks that Freeman Dyson was the smartest of them all. If you read you can probably read that. Actually, I was recently in contact with Freeman Dyson. I sent him an email. I think he's 94 or something. I said, he will never answer it. Didn't take more than an hour and a half. Yes, this is fine. Yes, you have my full approval, including this in a review paper. Now, the modern view of the world that emerged from Maxwell's theory is a world with 2 layers. The first layer consists of fields satisfying simple linear equations, Maxwell's equations, Maxwell-Lorentz equations, which imply superposition, interference. The 2 layers are connected because the quantities in the second layer are quadratic or bilinear combinations of the quantities in the first layer. Quadratic, bilinear in the fields. Those are the observables, not the fields themselves. And but we can make easy identification of the field by the antenna current. To calculate energies or stresses, like the one I just showed, you take the square of the electric field strength. You take the square of the electric field strength. This is not the electric field strength, that's the square of the electric field strength. And you can measure energy. And this is used, for instance, in radiometry, when you measure the common microwave, the cosmic microwave background. The receiver is so simple that you can't believe it. It's just a single resistor. Actually, 2 resistors. This is the Dickey technology, Dickey trick. You put the receiver and you absorb any radio that comes in at a certain frequency band, a certain region, and you measure how much does the temperature increase in my resistor, and we compare that with the calibrator. You wouldn't believe it, but that's very sensitive measurement. This is called radiometry. Is there energy or is it not energy? You concentrate on one of the 10 observables of the electromagnetic field. You design a detector. This is the trick. That the field contains all these quantities, as the energy, linear momentum, angular momentum, whether you like it or not. It's you who decide by designing your detector, your antenna, and the decoding, whether you study the energy, whether you study the linear momentum, normal radio, or the angular momentum, like the spin, which is part of it. You design your antennas to select a certain, to measure a certain observable of the electromagnetic field. So it's not determined at the transmitter end, but it's determined at the receiver end. This is closely related to the measurement process. So, the field of angular, correct. So, the unit of energy density is a joule per cubic meter, the one I just showed you, energy density. And therefore we say that the unit of field strength is the square root of the joule per cubic meter, because the energy is measured in joule, and then of course the field strength must be measured in sort of square root of joule. I think it makes a little funny comment about it. This does not mean that the electric field strength can be measured with the square root of the kilometer, which is sort of funny. It means that classical field strength is an abstract quantity incommensurable with any quantities that we can measure directly.
And this is quite natural from this photon point of view.
Yes, you're right. Yeah.
The wave function is
Because there's nothing.
Model the square root of the wave function.
Absolutely. No. There's nothing sort of field-like in the photon. The photon picture is much better. Yes, I agree completely.
What about electrons which are accelerated in old-fashioned TV sets? Just the difference of energy is due to the electric force, and which is proportional to electric field, not to the square of the electric field.
Yeah, but no, I'll come back to that. What you do, you have to look at the equation of continuity, and the equation of continuity for the force is the conservation of linear momentum. And you see that linear momentum, the field linear momentum, and the mechanical linear momentum is conserved if you have a constant input, and if you evaluate the mechanical linear momentum induced by the field linear momentum, you get the Lorentz force. That's how it works. But it so happens, this is why I say it so happens that, yeah, you have, for all practical purposes, in the TV or engineering expert, you can set an identity between the electric field and the linear momentum. But if you want to do a very careful analysis and avoid mistakes, you have to remember this. Doesn't change anything very much. But here I put together a table which compares the linear momentum density, for which I use a lowercase vector g with a subscript field, which is the Poynting vector s. G is s divided by c squared, is called. And with the corresponding angular momentum density, which has to be around a certain moment point, because you know it's the torque. So, this is this quantity, and this is the definition of that. They don't even have the same SI units. So this is, you see this is Newton's seconds cubic meter per cubic meter, and this is Newton second per square meter per radian. So they don't have the same, so they're different physical properties. This one fulfills this equation of local equation of continuity, and if you integrate that over all space, it gets the global equation of continuity, and this will give you the total mechanical linear momentum, and the time derivative of the total linear momentum. That is, how much force does my electron experience when it's subjected to this radiation field? And it turns out to be the Lorentz force. But there's some corrections too, but to the first report, there's some relativistic correction, for instance. So, and you have, here you have the maximum stress tensor, or actually the negative of it, and here you have the more complicated tensor. The interesting thing is when you look at it very far away, for a completely general set of sources, it falls off as 1 over r squared, which means that we integrate over a large sphere, we get something which is constant all the way to infinity. That is known as the radiation arrow of time, discussed by many people, including Feynman. We recently showed, and actually this paper, that for a general, completely arbitrary sources, currents, and charges, including also possibly magnetic charges and currents, you have exactly the same fall-off, which means if you integrate the angular momentum density over a large square and do that very far away, it goes to a constant, which means that the angular momentum is also lost forever. So there is an angular momentum arrow of time. The typical phase factor of an ordinary radio wave where linear momentum is focused on is something which has this. It propagates along the z-axis and it oscillates with omega. With angular momentum, you can prepare it in such a way, using certain antennas like cross dipoles, we'll come back to, that you have an extra term here. So this is an integer, m belongs to z, 0, then we back there, plus minus 1, plus minus 2, plus minus 3, blah, 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 blah. And each of this is unique. It's called the topological charge of the beam. And you cannot destroy it. It's like ordinary charge, you cannot destroy it. Which means when you leave the transmitter, and just around the transmitter, you can dope, as I mentioned before, your radio wave with angular momentum, but if you do it in such a way that the angular momentum is just one integer, which means the rotation of the phase is precisely 2 pi, or n times 2 pi, or minus n 2 pi, then you can discern, even though you have the same frequency, and here you can separate it. This is very trivial to analyze that. You just you measure the field around your beam, and you make a Fourier transform around in the azimuthal angular range, and the Fourier transform of that is the angular momentum. So
to discover this integer, you have to integrate over.
Sufficiently large, not all. But this is true also for this antenna. You cannot have an antenna which is 0. So the linear momentum is an average over half a wavelength. So that's not a local measurement. So you, in an ordinary radio, you integrate over half a wavelength typically. In this, you take that half a wavelength and you turn it around into a circle, and you measure around that half a wavelength or a portion of it. If you have a shorter dipole, you separate. I can use the black. If I have...
Well, this integer comes from the harmonic analysis over S1.
Yeah.
But the trouble is that you may have two functions which are identical over a big piece of circle,
I'm
but still they have very different.
No, I will show you how you separate that. And I have a numerical experiment. Yeah, we have done it experimentally. We published a paper on it. So it's possible to do it. Other people have published papers too on it, using it in real communication situation. So what you have here, if you have an ordinary radio, can I?
But every function on a circle may be decomposed into a superposition of those sinuses and cosinuses. But you may take two functions which are identical, for instance, on 1/4 of a circle, identical, but they still have completely different composition of those amps.
Yes, and by doing the Fourier analysis, you find which M are present, which M are not present. You get a spectrum, and this is how you identify the signal. I'm sure you. So in ordinary radio, we might have a parabolic antenna here, say, and some kind of dipole or even a cross dipole. We transmit, and we have what we call an antenna pattern, which is nothing but this G field, because it's the linear momentum per cubic meter, or it is the pointing vector, which is the same thing. Divided by c squared. Now, if I put the receiver on this side, I don't have to have an antenna which covers all of that, which could be hundreds of kilometers or even more than that. It's enough that I sense some part of it, so I can identify the wavelength, the frequency. This is what you do. You put your antenna here, you have your antenna here, and you receive a little part of it. That antenna might have its sensitivity like this, so it's this part of the whole transmitted thing. Now, if you do that in angular momentum, instead of having that, which gives you a linear distribution, if I look over here, I see that the intensity goes something like that, right? And you don't have to cover all of this to get your information. You can cover just that if you have a good receiver. I get the signal, it's strong enough for me. Now, in angular momentum, the pattern looks identical, except that it's not on the line, but it's on a circle. So that's where it's like a Bohr-Sonnenfeld condition. So, angular momentum is located like this. So I only have to measure along the circle segment of that. Now, so this is a way of doping it when I say, oh, I number 15 or I number -7.
Am I wrong by saying that if I have an antenna, I want to send a signal?
Sorry?
I want to send a signal to someone. Then I pick up an M of my antenna.
Yeah, well, when you
If I
want...
want to code my information in your angular momentum, then I pick up some M.
When you transmit, you only have one N here, namely N equals 0. You have no other options. You can have polarization, but I don't talk about that. I talk about the orbital part of the N.
Now you want to
Yeah, now I can send one with N equals 0.
Yes.
At the same time, I can send one with N plus 1,
Precise.
and then I can send
Yeah,
one...
but the M is picked up by the position of the antenna.
No.
This is angular momentum.
No, it's the same point. It's a 1 point. It's 1 point in distance. This volume contains all the
And
N.
this is picked up. Suppose the information is sent by the array of the cellular phone antennas, right?
But yeah,
I
it
want
doesn't
to pick up the information in Pernambuco.
No, you cannot.
From
Now I'm talking about a point-to-point communication right now.
Okay, so that was my point. So I cannot, because that's what I mean, that it fixes the receiver and transmitter.
So if I have one antenna here and another one there,
Okay, but
which is a link.
then you would have to use a complicated decoding on this other antenna.
No, it's much simpler than today. There are tricks today when one tries to do this. Is called MIMO. That's very complicated. That requires a lot of computing, post-processing. This does not do. We do the processing already in the physics, so to speak. So if you have one antenna here and one antenna there, you only have one frequency, you only have a fixed bandwidth. Authorities say, this is all you get. Now you try to put as much information as you can in that. And what the people have done so far is using all kinds of engineering modulation and
Yeah,
tricks.
but suppose you are not sitting on this other end.
No.
You are sitting in Pernambuco, you have to send it again.
Yes, well, you have to
So
send
then
it
you
to
have to
another
do
antenna.
something on this other tower.
Yeah, but that's true for this antenna too. If this is, this ordinary radio
But
antenna.
it's much simpler because
Yeah, of course, yes. Yes,
because
yes,
it's
yes,
only,
yes,
it
exactly.
only needs the distance.
Yes, I
But you have
It
less
doesn't need
bandwidth.
the phase shift comes back from the distance, not from a complicated.
So if I transmit my beam here from Warsaw to Stockholm, and I'm sitting in Pernambuco, I will not hear it. Even your this, I have to transmit signal in the direction where I want the signal. If I transmit 0 watts to Pernambuco, I will not hear anything, regardless of linear or angular movement.
But the cell phone system does not work.
No,
this
this
way.
is no.
Each tower sends something. There's no point of. Each tower has to send something,
Yes,
not knowing from where it has come.
exactly. and this
Depends,
is-
there are also transmission between the BTS.
Well, so let me emphasize that this is a research on the physics level. We're not even approaching making a suggestion on how to be used for mobile telephones.
Okay.
We have implemented it for a fixed link
I
in
know
mobile
it. At
telephones.
that
Yeah.
stage, I'm
Well, but
This
I
is-
think that the main point is that the problem is with the free space propagation, which is a narrow bottleneck. The
Yes.
rest is done with light waveguides, which is not a problem.
No, well, it's becoming a problem sooner or later. Yeah.
Obvious.
So what we have today, we have the
You
fourth.
have destroyed this beautiful picture. Let me do one simple remark, namely, your analogy between measuring this on a line and on a circle works perfectly, provided the wavelength is very short with respect to the
Yes,
length.
yes.
This means that you have to consider very large M's. And
No. The wavelength is determined by omega k, not by n. So what you have here is that a good antenna, linear momentum or pointing vector, a typical antenna length along one axis of linear length is on the order of lambda 1/2, right? And so you must have an antenna which is lambda 1/2, and there is a technique now used in mobile telephone system called MIMO, multiple input, multiple output. Then you have two antennas, but they have to be separated by 1/2 of the wavelength, which is nothing but the Heisenberg uncertainty. Now, in angular momentum, you have to have this, that the circumference, 2 pi r, should be on the order of lambda 2, which means that the radius here is on the order of lambda 2 pi. So the spatial extent of this is much smaller than this, 1/6. So, but you cannot get below that. This is the PDX equal n plus 1/2 pi, which is the old quantum theory quantization condition. It comes precisely from this. Bohr and Sommerfeld showed, it said, well, we have to have it in such a way that if there is an atom and the wave function, that the angular momentum of the wave function must be single valued, therefore you have this quantization inclusion. This is precisely what we use. This is a classical thing.
So it's about 2 centimeters for modern phones.
So, and you can actually associate this with a quantum operator. This is the quantum operator for linear momentum, and this is for the angular momentum.
So it fits my body.
10, 20, 30 years from now, we are doing fundamentals. We're trying to build up a new physical area.
But even today, 2 centimeters
Yeah.
fits my body.
Yeah. The interesting thing is that the angular momentum density is not a vector, it's a pseudo-vector, or equivalently, it's an antisymmetric rank 2 tensor. Like, you know, the B field, if you think about the field tensor, you have E, which is a vector, but you have 3x3 matrix representing the magnetic field, because the magnetic field is a pseudo-vector, not a vector. This is also a pseudo-vector, so we can equally well identify it as an antisymmetric tensor, 3x3.
Yeah, excuse me, I just want to come back to your question. I think he meant something which we know, that to distinguish different components of angular momentum, or by that matter any quantum number, so to speak, carried by a wave function in quantum mechanics, on the range you measure it, it has to acquire a considerable phase,
Yes.
right?
Yes.
So if you measure it on a very small angle, then m has to be sufficiently large that the phase acquired is of the order kind of 2 pi, so to speak,
Yeah,
right?
this is the rotational correspondence to the,
And so
you know, yeah.
ultimately your remark was kind of correct.
This is my question.
Oh, thank
This
you
is,
for it.
you know, this is for linear momentum, but for angular momentum, it's something similar.
Yeah, exactly. Well, in this way, yeah.
Yeah.
Mhm.
Precise.
But the nice thing is that you have an angle, so it's recurring all the time, so you can make that error as small as you want, because you know it's at 2 pi. There's nothing, the relative error of the phase is not well defined, only the absolute, because if you have comparing 14 and 16 degrees, or let's say 0 and 45 degrees, is that a small angle? Then you take, 5 degrees divided by 45. You get 1/9. But if you add 45, you add 6 times 360, you get something much smaller. So the relative error goes down, and this is still being discussed in the literature. This is not fully understood yet. The thing is that this is an even in C, but it's odd in parity. So it's an odd parity pseudo-vector, which is the same thing, of course, but it's an axial vector. So that makes it a little bit more interesting, and you have to be careful. So, but as I said, using angular momentum much more difficult than linear momentum. Marconi, he realized that if I'm going to be rich, which he probably wanted to be, I cannot just use the energy. Here I am, you know, he has some kind of very simple generator, dot flashes or something. I'm on the radio band. No, I'm not. 1, 0, 1, 0, Morse, all the frequencies were covered in Marconi signal, and said, this is not a great idea, because I'm the only one who can use it, because I will interfere with others. So he started to think to move back to this. So this was it. This on-off signaling. This was the first way you did it on the optical fiber. Light on, light off. 1, 0, 1, 0. Light on, off, on, off, on, off, 1, 0. But then one realized that's a very clumsy and very resource-wasting thing. So he said, if I do something more clever, if I divide the spectrum into various frequency bands, so I communicate with my people on this frequency band, and other people communicate with that people on the frequency band, then we are happy again. And that is nothing but dividing it into wavelengths, which is nothing but dividing it into wave numbers, which is nothing but dividing it into wave vectors, which, according to quantum theory, is nothing but dividing it into different linear momentum, h bar k. Here we do the same with angular momentum. This is how a linear, circular polarized wave. You take a snapshot of the beam. We have, let's say, we have a way of estimating the electric field, or correctly speaking, we measure the antenna currents in 25 small antennas. This size, you cannot have zero size antennas, because zero size antenna gives you absolutely nothing. You cannot have points. So then you see that all the field vectors at one given instant is pointing in this direction. Then you wait a little bit, for instance, a quarter of a period, and then all of them have rotated into the other direction. And of course, if you have simultaneous of this and others which rotate the other direction, you have two possibilities. This is the polarization. This is how polarization works. Now, if you do the same in angular momentum, it looks a bit more complicated. If you measure the instantaneous directions of the currents in antennas distributed like this, or as I will come back to later, you can have a single monolithic detector using spintronics and orbitronics, where you get all this information. It's a two-dimensional information. This is one dimension. You see that I don't have to wait. This now contains both spin and angular momentum. The orbital angular momentum is manifesting itself already at time et delta t equals 0, because this, along this direction, this is the azimuthal angle phi. Along this direction, I have the vectors pointing in that direction and here, so I just compare not in time but in space. But then, of course, if I have it also polarized, if I look at each individual one, I see it rotates 90 degrees, 90 degrees, 90 degrees. So it's superimposed on the orbital angular momentum, we have spin angular momentum. So for each orbital angular momentum state, we can also have spin 1 and -1, or left-hand and right-hand polarization. So by using polarization on top of this, you double the capacity. Yeah. So, yeah, and this is another way of looking at it. Yeah, the important thing here is that to measure polarization, we have to measure the direction of the E field, or more correctly, the direction of the antenna current vector, at 2 different times, which means that the beam that I receive must be temporally coherent, or have a certain coherent time and coherence length, which is at least half a period or something like that. This is not necessary in angular momentum, because then I can measure the same instant. However, I have to measure different space points. So here you have to have spatial coherence. So it's like spin, polarization is time-like, whereas orbital angular momentum twist is space-like. And here's I would say you can go to archives. We wrote about 35 pages or so. We derive everything from the beginning. Very simple. It's like a textbook. I don't think I will even be able to publish it because it's too simple. But then again, it's, electromagnetic field theory is complicated as it is in classical. Now, so by having a 2-dimensional structure which allows us to measure this structure, the ideal thing would be to have a big sheet, a conductor which is like a drum skin or something like that, like a circular plate of metal, and have, being able to identify the patterns of currents in it, because the patterns of currents will be different for different OEM. And if I have a superposition, I can Fourier transform that pattern. And one way of doing it is to have a kind of membrane like this, and then you shine a laser and you measure the distortion in the laser, and that's 2-dimensional. It's a pattern recognition technique. It was used recently in Vienna by Anton Seidlinger's group to transmit pictures across Vienna of Mozart and Holzmann, I think, using OEM. And they had a 2-dimensional detector, because you cannot measure linear momentum by a 1-dimensional detector, regardless of what kind of detector you have. You have to have 2 dimensions. Now, as I said before, instead of having one 2-dimensional antenna, I can have a large set of 1-dimensional antennas that I put in discrete points. That is sampling in space. It's a sampling in 2-dimensional XY space, like we do in radio telescopes. So we ran a numerical experiment where we had a ring of antennas here, 8 antennas and 16 antennas there, and we fed them in a certain standard phase way to approximate a perfect parabola, which is called emulated parabola, and of course you get a pattern which is very parabola-like. And this is the technique that is used in the radio telescopes. They like low-fi. They don't build, big steel constructions which are hundreds of meters across. They build small antennas, and they sample them, and they combine them into a virtual parabolic antenna. This is what we do here. So this is precisely what you get from standard antenna theory. What you see here is the linear momentum density, the pointing vector. It's not the angular, which is completely different. So, but then I said, this were 2 undergraduate students doing this. And I said, let's now change the phase of each of these antennas in such a way that when you move around, you have shifted the phase by exactly 360 degrees, and you did the same here. Then you get this linear momentum pattern, but when we analyze the electric field, you see that this electric field and this electric field are opposite precisely as you expect from OEM. So we did other tests, and we have repeated this in the laboratory, of course, confirming precisely that this works, and this is standard technology nowadays. So in this case, we have L equals 0, L equal 1, L equal 2, and L equal 4. But you see, we're using a discrete representation of a continuous surface, and that's when the sampling theorem, the Nyquist theorem, the Nyquist-Shannon theorem comes in. And it says that in order to represent OEM of state n, you must have at least 2n plus 1 antennas. So in this case, we are doing m or l equal 4. We should have 9 antennas. We only had 8. So that's why we start to see sampling errors. Now we can combine this. So we took one ring with one quantum number, another ring, the outer ring with another quantum number. So we made a coherent superposition of 2 angular momentum states, radio, and we found this. This is our radio experiment run on the computer, verified later in the lab, and also out in the field, in the real world. So the maximum intensity is this. Now it's only half a percent. So you see this focus. And when we have other combinations, we get very small, and you only have to measure this one because the amplitude and phase in this repeats itself identically this 3 times over. So by measuring this, the only thing you do is to lose the signal, but you do that also when you measure with a small antenna a wide beam of linear momentum radiation. These, by the way, are figures that were produced by using Laguerre-Gauss modes, which is used in optics, and these are the ones that we realized in radio, and you see they are perfectly. So we can also then, by controlling the phase, we can also twist the antenna, or turn the antenna like this. So without angular momentum, we have this. With angular momentum, we have this hole, and this is the picture you saw on the first page, but reversed, because I think it looks better looking right. I don't know. It's just not his mistake. Now, why would you need such a thing? Well, it's very good coronagraph. If I want to measure radio emission from the solar corona and I want to block out the sun itself, I design my hole to be half a degree, which is the photosphere the size of the sun, and I see everything around it. So there are lots of new things that you can do. This we published in Physical Letters 99, and it's been cited quite a lot. Not 99, 2007. The nice thing with this is that the third and the fourth authors are undergraduate students before they even got the first degree. We sent the article to Physical Letters, it was accepted immediately without any comment. And it ended up on the first page of it was a selected paper of the week, and these were 2 undergraduate students. This is unique in Swedish physics. I'm sure it's not unique in Polish physics, which is much better, but anyway, we are proud to say.
And what is their fate? After 10 years, they continue to?
Yes, one is leading antenna development in a company, and the other one is working in a research group doing magnetic field studies. But there's another story which I will not tell, which I told you, which is now. Since linear momentum density is something completely different than angular momentum density, I had another couple of students, because I've been teaching the course in advanced electromagnetism, electrodynamics, classical electrodynamics for nearly 20 years, and this is the last course, this is a 5th-year course before they leave and go to research or industry. But we can have a rather high level of requirement for them. So this is results of 2 students, 2006, 2007. Here is result of 2 students, 2012. I told them, now here, this is the linear momentum density shape, because the standard, this is a standard solver, the standard piece of software which is used everywhere. It's very popular, very, very precise. But the designers of the Maxwell solvers have never thought about plotting the angular momentum. I wouldn't be surprised if they might not even have thought about it, even heard about angular momentum. So they always plot the linear momentum, or as they say, the pointing vector, or as radio engineers say, the antenna pattern, radiation pattern, the antenna diagram. But the diagram for the other quantity, the angular momentum density, and I'm sorry, but I have to flip back now. So we saw up to now the plotting of the magnitude of that and its angular distribution in the spherical coordinates. This is what I showed you. Now, I asked them to plot this, because this is a vector, and I wanted them to plot it in such a way that we integrated around a circle, around a crossed dipole in the plane. So, we put a crossed dipole, half a wavelength, and we calculated this quantity.
Phase shifted.
Yes, yeah, of course, yes, yeah. Coordinate change, yeah. And they took an instantaneous picture sort of what is the direction of this vector, which is angular momentum per cubic meter, and they all point in the same direction, right? So when we integrate that, we get angular momentum, we get a torque. So if everything is right, if I put a cross dipole like this, and I have a circle of free carriers, which I can easily approximate with a ring of copper, then that ring of copper should start to rotate mechanically. Now, this is similar to the celebrated Einstein-de Haas experiment, where he did this work. So I suggested this to my French colleagues, and here is the result. Yes, it works. Perfect. So we put, this is an antenna chain, we had a ring of copper, and this is the theory, and this is experiment. Published in Phys Rev about a year ago. That is, this is 870 megahertz, and this is quartz wire, very low internal friction wire. So the whole thing starts to rotate. Actually, we did the major hurdle of this in the sensitivity is that.
By się nadawało na festiwal nauki.
Sorry?
We have such a major science popularization trade or whatever, a festivity of science or science picnic. Such an experiment would be very well suited.
Yes, but it's very difficult to do.
I know, I'm joking. I appreciate that, of course. But
I don't know how many months you spent or they spent on it.
yeah, sure, but it's amazing,
It
amazing.
turned out that we made some calculations, and the group here had a long experience doing this, torsion pendulum sense. And so this was in open air, so the air drag was the limiting factor here. But if you pump that out and you put it in a vacuum chamber of reasonable good quality, we calculated the sensitivity. How far away can you be to detect this rotation from the source with a power of, in this case, I think it was 40 watts or something like that. It turned out to be somewhere in our galaxy. Yes, it's cosmic test. You see? And now if you can do that in a nano mechanical, like the guys in Vienna, like the Sassenmeier, I think there is fantastic. But I'm not calling this is research. This is not product development. So, now time for theoretical physics or time to stop, Mr. Chairman?
Still 5 minutes.
I would need 15. Is that possible? Well, I start. Anyway, you know all this better than I do probably because you're theoretical physicists and so. Let's take a field, a beam is always a wave packet. It's a superposition of various electric plane waves because a plane wave does not exist, it has infinite energy, you know this. So you have to combine plane waves into a wave packet, like in quantum mechanics, superposition. And each of these waves that you combine with different amplitude and phase to form a certain beam, if you assume that when you describe it in cylindrical coordinates, you can separate the radial, the azimuthal, and the longitudinal like this, which is maybe, well, you can always do it, but sometimes it leads to nonsense results, as you know, because you cannot get, very often these two are combined into a function where you cannot really separate. But as a matter of sort of discussion of matter of principle, let's assume that this now is essentially a single longitudinal k vector, the kz, and it has a slowly varying envelope, and this is the smallest parameter, so this means that it varies very slowly. When you Taylor expand this amplitude function, it falls off very quickly, and then you only need the first term, constant term of that, a bit more like that. In purely monochromatic sense, it would be a constant, but such things as, of course, do not exist. This is again the precision. And you do the same with the time. And
Where's T?
It's a mistake, it should be Z.
yeah, yes, there should be a oh, yeah. I forgot to say. I should have done it this morning. Sorry.
Okay,
It's correct in the paper. I noticed.
Okay, go ahead.
I beg your pardon.
That's all right.
Shit. No, I saw it. I gave the similar seminar. I saw it. I must fix it. But that shows that, yeah, of course it's the same. Okay. Yeah. So you have this, the longitudinal, the temporal, the radial, and the azimuth. This longitudinal and temporal are very slowly varying, so it's essentially monochromatic in time and things like that. Whereas any azimuthal function, because of the single valueness when you go around, it can always be represented by a discrete Fourier transform, or as we say, Fourier series, unless it is totally nonsense. I mean, white noise, you cannot Fourier transform white noise, it's not L2, things like that. But anyway, we do that. So that means that any variation in phase you have around will produce a spectrum, and if you have a variation which is precisely, smoothly, linearly increasing from 0 to 360 degrees, like we had in our antenna experiments that I showed the colorful pictures of, then only this for m equal 1 will survive, and the sum will be reduced to 1 term, and that's it. But this is also wrong, it shouldn't be an operator error. But you can actually do it like that. And I could show that and have, but that will be next time. Ivo has done it beautifully. This is where I got it from. He's done it beautifully in the YouTube co-author something, sorry. But, so you, I mean, if you want to ask a question about it, don't ask me, ask these experts. This is very elegant. So, you recognize this from quantum mechanics. So, electromagnetic waves are, in a sense, the wave functions of photons in first quantization. So what you do, you pick up that. Now, with a single, each of these EM now have an index M. I pick this, I take that out, I take one here. This is essentially E. If I take one N in the series, it will be EM, and it will be proportional to something like this, a constant time this. And we have this, as I showed you in the table. But if you don't prepare it, if you have a random variation of your phase around, this spectrum will be extremely wide and it will be noise-like, and it will be very difficult to make any predictions about it. You know, it's like white noise in azimuthal space. So, and if you do that, and you see that this is 100% classical. There's no assumption of any quantization except the fact that you have this quantization that was used by, this comes automatically. This follows 100% from Maxwell's equations, nothing but Maxwell's equations and Maxwell's equations below. Still you have a sort of quantum feeling to it, if I may say so, which is nice.
No, the other problem is the Planck constant.
No, but no, I wasn't. I multiplied here and divided somewhere else. I just replaced 1 with h bar over h bar, just to make it more familiar.
That doesn't come out.
But otherwise, it wouldn't have the right dimension. This has dimension of angular momentum. You're right. The brightest audience I've had in a long time. I can't find all the errors. I'm sorry about this. This one should not be. Should be L. This is the average of the Z component of the angular momentum. Now, if I have a special phi, I told you I can have a random distribution of phase variation over azimuth, but if I have an angular distribution of azimuthal angular distribution in this azimuthal part, which is like this, where this not necessarily is an integer, but an arbitrary number, even a complex number. That's for artificial, but it could be even an irrational number. This is now very common when you observe things in radio astronomy. You have a source that you suspect, this source probably emits angular momentum, has a certain angular momentum spectrum to it. So you have this, and this is nothing but k, the phi component of the k vector times the radius, and this is the angular momentum. This is the angular momentum. We made an experiment in Uppsala where we had this quantity k phi rho alpha equal to minus 1.12. And you don't get a single eigenstate, but you get a spectrum of eigenstates. And the spectrum of eigenstate comes from the fact that when you plug that into this formula here and calculate the standard way by integrals of the CM, the various Fourier components, Fourier meters for this arbitrary alpha. This was first given, I first saw it in the paper by Barry, but I realized I found out that it was published before, so Barry from physics, mathematics, were not designing years in this. So this means that if I have an arbitrary K phi rho, an arbitrary angular momentum in my beam, a distribution of angular momentum, and I do a spectral analysis in phi space, I will get its discrete angular momentum complete states like this. And that means, now, this is the idea behind radio communication. Doing too much time. Let me end with this then. I have not more, but let me end with this. Again, back to Marconi. He was all alone, so he transmitted from 0 hertz to hundreds of megahertz probably. Then he said, no, let's rasterize this frequency axis. So we have one radio station here, we have one TV channel there, another one there, a third one, a fourth one, and so on. And you sell these, you take money for them, very expensive. Then one realized, this is not enough, we are filling up rapidly, so this is now with the spin +1, left-hand polarization, say. So we do the same thing with the right-hand polarization, and we can reuse the same frequency once again. This is used in TV. You go to Sweden, you see TV antennas which are like that, you see TV antennas like that, same channel, different, same radio channel, same radio frequency, different TV programs. Polarization. Now,
unfortunately, equal is story.
right?
Unfortunately, equal is story. TV program.
Yeah.
Independent of polarization.
Yeah. Okay. I was in the physics mode. I wasn't in the mode. Sorry. But you saw that spin angular momentum is this is a 1 bit, it's +1 to 1. So you have double. But now for any given frequency, let's say 96.6 megahertz in Uppsala, which is called the radio channel, I can have one channel with transmitting on that frequency, same polarization, everything the same bandwidth, nothing else, except I add m equal 1 to 3. Here is alpha, is m equal 3, but you know in discrete Fourier transform you get frequency bins, and you get these frequency bins because this is again a kind of frequency. It is how much does the phase vary as a function of phi, whereas this frequency here is how much does the phase vary as a function of time. The phi dt is frequency, the phase phi is angular momentum. So this is linear momentum, angular momentum. We have k and z, L and phi. So that's how you can do it. And we did an experiment, and it's been accepted. Here you can get it. We are just waiting for it to appear finally edited, but you can refer to it. It's referable, and we already see people refer to it in the literature. It was accepted on 18th of May. We had a link which was 6,000 lambda, it's very far away. And this was done together with a microwave company in Italy who provides solutions for the telecom industry, including the mobiles. They wanted to see how to do this. And this is the antenna we had. You can go to the paper and read the details about it. This is the waveguide, and this is the emitter. We had a parabolic antenna. We changed the phase precisely 360 or 720 or something like that around. And so this is the measured intensity. You see the little hole in there, but it's enough to measure a little part of that. You get the information. So the hole is very small, and then we measured the phase in this standard way, measuring the phase of the antenna current, and we see that it varies around like this. And this is a mathematical idealization, a mathematical model, and see it works like that. And then we made a Fourier transform of this, and around here, and we get that angular momentum spectrum. And the same for 0 and -1. So that means that we had one -1 channel, one 0 channel, one +1 channel. So we transmitted the same amount of information as they do today on the M equals 0 channel, and we did it 3 times over, and here is what is called a constellation diagram. This is what is used in radio communication microwave technology industry. It tells you how it works, and this is a perfect pattern for a standard microwave link used in mobile telephone today, and we managed to triple that without using anything else. Absolutely nothing at all except the angular momentum. No polarization tricks, no modulation tricks, no other thing but just angular momentum. And so this is what is now published, and I think that is the first paper. Let me put this on, and I tell you that if you look at the radiation that comes out of a rotating black hole, where you have perimetric, and you calculate the angular momentum of the radiation as angular momentum, so this is a way of identifying the radiation from very near a black hole, not like the black hole, but in the accretion disk around the black hole, which is a strong emitter. This is for Sagittarius A star. This was published in Radio Physics, and it was a lot of interest in this. And we are carrying on this now. We talked about it last night. So it can be used both for communication and for astronomical astrophysics. Sorry for taking so much time, but anyway, thank you for your stamina, for your patience. Thank you.
I have a question which may be totally stupid. I apologize.
Well, those are the best ones.
But in astronomy, we plan to measure two types of waves: electromagnetic waves and gravitational waves. And in the case of gravitational waves, we expect that the signal which we measure decreases linearly with the distance of the source, because we measure directly the amplitude and not the amplitude square. And is it because waves are different, or is it because, as you stressed, the experimental setup is different?
First of all, the electromagnetic waves are vector waves. Gravitational waves are tensor waves.
Yes.
So that's a difference. The other thing is that when you measure the electric field, which you cannot measure, as Freeman Dyson said, and he confirmed that in an email, I can show it to you. So don't blame me. E at far, falls off as 1 over r. But we cannot measure it. So we take E cross B, pointing vector, and it goes as 1 over r squared, and then you integrate that over the r squared, the r is the phi, sine theta, d theta.
Yes, but in the case of gravitational waves, somehow we measure directly the amplitude.
But yeah, I don't
so
know
we
too much
measure
about
something
this.
which corresponds to this.
Maybe there's something we should do. Show you on this. What are the observables in gravitational waves? I have no idea.
When gravitational wave comes, just the antenna expands and shrinks.
Well,
so
here you can put a charge on a somewhere and on.
What you have to do.
And you observe that on a pendulum, you charge pendulum, and you observe that when the electric field is passing, it starts to
As you
move.
said, you had a very good question. Well, we just measure the Lorentz force, and it's just the E field, but it comes from the fact that we have to analyze the postulates of electrodynamics, Maxwell's equations, and you find the conserved laws, and you find the conservation of linear momentum, which set things into linear motion, and when you plug that in, it turns out to be the Lorentz force. Lorentz force follows from Maxwell's equations by symmetry principle. You don't have to assume it. It's built into Maxwell's equations already. And you have to do a very similar analysis of gravitational waves, find out what are the conservation laws, and then apply those conservation laws for your experiment. And I would suspect that you will get something similar, but I cannot say. Because, just a second.
The conservation laws are the same.
Yeah.
From the symmetry.
But still we have this basic difference, right?
Well,
At the moment we are
we don't have
not
we are
measuring
not measuring
anything, but
anything.
we only hope to be able
Well,
to
but
measure.
I
Hope
thought that the
that
basic
possibly we
understanding
will be
is how.
able to possibly.
Yeah, but how about this LIGO, LIGO?
Yeah.
The distances between certain objects, but in
Yeah.
these earth-based telescopes, you rather measure constellations of.
Let me take this antenna, and I've taken an electron in the antenna, and the simple picture, which is correct, if you do a complete analysis, you do the, and then apply it to a single electron, which was final speciality and always applied everything to a single electron. Of course, there's an ion, but it's infinitely massive, so it doesn't recoil. So you see, and what you get when you have dp, dt mechanical on an electron, the electron starts to move because this is almost, well, it's essentially. So in that way, but this is an approximation, you know, with something. So this is the fundamental difference, sort of philosophical.
Would be the same for gravitation?
Yes, this is my point. This is precisely my point. Precisely my point.
It doesn't mean that
So
you measure the electric
You
field.
think that you measure this, and everybody thinks that it works fine, but strictly speaking, you're measuring this.
Can I have another question?
Yes.
Because it is a beautiful part of research which is completely analog. You are talking about fields, currents, Maxwell equations, while basically at technical university in Warsaw we don't teach any more analog electronics or physics. Everything is digital.
Me. I even written the
You
book
know,
on this.
how come that in Sweden it's still possible to do something?
It's a bit colder.
No, this is very important because we train our engineers completely to process signals which are after analog to digital converters, right? Because it's so cheap, it's so easy, you can do it on computer, there are only bits and so on, so on. Basically, I don't think anyone is teaching nowadays how to build an amplifier or measure current or do things like that.
But you always need classical field theory. You know.
No, I understand that, but my question is sociological.
Yes,
How it comes that in Sweden it's still...
And I used that to argue to the university, and they said, you know, okay, give a course which was in our system 3 points, which is a rather small course. Now it is 10 points. It started 20 years ago, I expect it. And it was a course in classical field theory applied to Maxwell equations, where I tried to build the course in such a way that it was clear that this is essential for gauge theories. I mean, I even mentioned Yang-Mills theory in my, I even wrote a book about it that you all can download, and I don't get any money for it, so I can promote it. You can download the book where I do all these calculations, deriving the angular momentum and all that, and it's about 300 pages, and it's used in many universities all over the world, and it's now being printed by Dover Publications, but I have an agreement in the contract that I can put it up for free for students to download PDF file. Now, in that, I made a lot of effort because I like electron, I like field theory, I like this thing. So somehow the course got popular, and people all over Sweden went, how do you do it? And like you said, so we're lucky. Now I'm giving it up. I gave it to a professor in theoretical physics to teach it now starting in September because I'm out of the system. I'm too old. But it's a matter of, what I wanted to say is a matter of commitment also of the teacher. Push hard, push hard, push hard. And you have to make sure that you try the best you can. I don't think the course is very good. Other people think it is good. That's the point. So when you end up number 1 in the ranking of 120 courses, then you can be pretty sure I will probably get money for the course next year.
This is
But
not
it is
entirely true.
a lot of work. You know, you work
Sure.
like crazy.
Any more questions? No, thank you very much.